Hi, the 8.4 diagnostics, the more plots. So this time, the model diagnostics, linearized response versus predictor plots. So idea is not difficult. In linear model, that we would like to investigate the relationship between x and y. And if we make a scatter plot, it's clear that what we should do. So in this case, the relationship between y and x is nonlinear, and probably that we have to regress y on x as well as the x square. But for generalized linear model, since we have the link function, the situation is more complicated. So the point is that still we would like to have predictor value x on the horizontal axis, but the vertical axis that we would like to have the something, I would say z, so that if linear relationship is correct, then points are along some straight line. So in this way, if we can find such variable z, then we can see whether generalized linear model assumption is appropriate. So originally we have y, but the y is highly the transformed variable. So basically we use the link function to calculate it. So we have to use the inverse the link function to generate this z instead of response y. So z is called linearized response. So that if generalized linear model assumption is correct, then the relationship between z and x is linear. And the basic idea is that z minus eta is equal to y minus mu and the derivative. So yeah, so this quantity is calculated in this way. So okay, so in this example that we use the Galapagos Island data, that is the Poisson distribution. And the Poisson distribution, the log of mu is equal to eta. So d eta over d mu is equal to 1 over mu. So z is defined by eta predicted value plus the species minus mu, y minus mu over the log of this. So the d eta d mu. So that is 1 over mu. So if we use this z, that we can see the relationship between z. So this is the species, the transformed species, the number of species, and the x, the variables such as area or the area of adjacent island or highest elevation. So here the z is on the the vertical axis, and the horizontal axis are variables: area, elevation, nearest distance, and the distance to the St. Cruz Island and the area of adjacent island. So you can see there's some relationship between area and z. There's maybe some relationship between elevation and z. Relationship isn't clear here. Maybe negative relationship, but if these observations are extreme values and we need some transformation, then not entirely clear. And this one also not clear. Maybe this is one outlier and the others, possibly a negative relationship, but not clear. So you can see the relationship between the z and predictors. If we take logarithm, some of the graphs look better. And actually this is a good graph. The log of area and the z are linear, and log of elevation and the z is also linear. It looks others almost random. So we decided to go the log of variables as predictors. In the the chapter 5 that we use just the original scale, area, elevation, nearest, the SC RUZ and adjacent, but here that we decided to go with the logarithm. And actually the result is not really intuitive. If we used all the log of these variables, actually, and also we do the stepwise regression, actually the final result is just dropping the elevation. In the previous figure, it looks like the elevation is most or second most important variable, but actually, in addition to area, which has obvious relationship with z, actually other three variables are selected. So anyway, it's really hard to imagine the multiple linear regression. So contribution of each variable is not entirely clear, but in total, the linear combination explains why. Yeah, so this is the result. And you can see the residual deviance is 360. So this is much smaller than the deviance calculated in chapter 5, that is 716 with the same number of variables. But still, the 360 on the 25 degrees of freedom. So the expectation of this residual deviance, D, should be 25 if this model is sufficient. But the 360 is still very large. So probably that this model is still not enough to explain the number of species.